So, good afternoon to everyone. It's my great pleasure that today we are going to have the next session by Professor Malay Banerjee, and it is my great pleasure to introduce Professor Banerjee. Professor Malay Banerjee received his PhD from the University of Calcutta in Applied Mathematics under the guidance of Professor C.G. Chakraborty. Dr. Banerjee joined the Department of Mathematics and Statistics, IIT Kanpur, in 2008, and currently he is working as a professor in the same department. Before joining to IIT Kanpur, he served as at Presidency College, Kolkata, and Scottish Church College, Kolkata. So his research interests include nonlinear dynamics, mathematical ecology, epidemiology, and he is serving as associate editor for various journals like very prestigious and very reputed international journal like the Applied Mathematics and Computation, International Journal of Bifurcation and Chaos, and Mathematical Modeling of National Phenomena. He is also the editor for the Ecological Complexity, Theoretical and Mathematical Ecology section of the journal Mathematics. So it's really very much pleasure for all of us and a good opportunity to listen to Professor Malay Banerjee. So now I request Professor Banerjee to deliver his talk.
Thank you, Professor. Thank you, Professor Mukhopadhyay, for your kind introduction, and also I was thankful to the organizer for inviting me to deliver this talk. So let me share my screen, and you can see my screen, right?
Yes, Professor Banerjee, you can see.
And so can I plan for the talk for 40 minutes?
Yes, I think Megha. When is our next talk, Megha?
I think 3:30.
Yeah. So you can have.
So I'll finish by 3:25. So if there is some question, I can answer.
Yes, thank you so much.
Okay. Yeah. Okay. So thank you very much for your kind introduction. And in today's talk, what I thought I should talk about, that is my new research interest. So although the title of the talk is Effect of Slow Fast Timescale Timescale on Transient Dynamics. And towards the end, I'll talk a little bit about effect of the slow fast timescale on pattern formation also, because transient dynamics can appear at different systems. And first, I'll give you some example and fundamentals of this ecological modeling, where we are interested to see this kind of slow fast dynamics. So that's why, first of all, I'll talk a little bit about what is transient dynamics, and then I'll come to some aspects of slow fast timescale model, and then I'll go to the spatiotemporal pattern, and finally I'll make some remark on possible future direction of research, followed by the references. Okay, so this is the just a pictorial representation for different kind of interaction between interacting species, mainly between herbivores and their predators. So the point is that once we are considering some ordinary differential equation models for ecology, and in various journals we have gone through some examples that okay, this model follows this particular species, etc., etc. But one point I want to make it clear that mostly we are actually interested to model or capable to model the interaction between the trophic level, not between the particular species under consideration. And the idea is that in this picture, you can see that 4 different prey-predator type interaction, which consist of one as a prey species and another as a predator species. But it is very much clear that either lion or tiger, they are not restricted to predate only zebra and deer respectively. So as a result, if we consider the interaction between zebra and lion is a prey-predator interaction, so then the next question arises whether this lion have only one food choice or not. If not, then one may think about that multiple prey single predator model. But we have to keep in mind this biomass is not huge for any particular forest or any particular region. Maybe over the entire globe, the total zebra population can be considered as a continuum. but they are distributed at different disjoint locations. So better to think about the interaction between two trophic levels. And this is a particular data set which shows some sort of oscillation between the population density of two species, namely hare and lynx, and this data is collected over a 100-year time period. And based upon this particular data set, the classical Rosenwig-McArthur model have been developed, whose basic idea was to explain that once a stable coexistence equilibrium point is destabilized and some periodic solution comes up, then how a mathematical model can capture this oscillatory behavior. Now the question is that the dynamics, what we can see here, the main part is the interpretation of these dynamics. One can call it, in a rough sense, it is a periodic. Again, one can argue that this is not periodic, rather it is a aperiodic, or maybe it can be considered as a some sort of stochastic fluctuation. But what are the main causes behind this stochastic fluctuation or some fluctuation in the system? They are need to be analyzed appropriately. But from a crude sense, what we can try to understand, we can try to understand that whether a simple mathematical model which describes the dynamics between a resource and consumer, that can capture this oscillatory nature of the coexistence of two species or not, that is the main challenge. So in order to accept this challenge, or in order to model this kind of interaction, the classical Rosenwig-McArthur model have been proposed, and they have proved that under certain condition, this model is capable to capture the oscillatory dynamics. So here N stands for the population density of resource and P stands for the population density of predators. And it is assumed that in the absence of predator, prey population growth follows the logistic growth law, and rate of consumption of prey by the predator follows the Holing type 2 functional response. And it means that if there is no prey, then predator will go to extinction through starvation, and with the increase in number of prey, the rate of consumption will increase, but it should not increase unboundedly. Rather, there is a saturation level, and that saturating functional response is thus modeled by this term an by 1 plus ahn. Of course, one can ask the question that how you have chosen this function. Answer is that there is some mechanistic way out through which we can derive this functional response, but within this talk I am not going into that particular part. So N is the resource population density, P is the consumer population density, may be considered as a population density of prey and predator, T is the time, and interpretation of other parameters are listed here, and I am not going through each of them. So for mathematical analysis, and in order to reduce the number of parameters, we can convert this equation to equation in terms of x, y, and t, and the non-dimensionalized parameters alpha, beta, and delta, just in order to reduce the number of parameters involved with the model. And then if we look at the equilibrium solutions, then this model possible equilibrium. One is the extinction equilibrium, another is predator free equilibrium, and this one is coexistence equilibrium point. So using standard stability theory, one can determine their stability properties, and it is clear that once this predator free equilibrium point is stable, then this condition is satisfied, and once it is unstable, then coexistence equilibrium point bifurcate from it through a transcritical bifurcation, and this transcritical bifurcation threshold is alpha equal to 1 plus beta into delta. And this is an important point to note, that the threshold value at which coexistence equilibrium point loses its stability, that is also the threshold for the transcritical bifurcation, and this particular coexistence equilibrium point bifurcate from extinction predator free equilibrium point through a transcritical bifurcation, and this coexistence equilibrium point destabilizes through a supercritical Hopf bifurcation, and that supercritical Hopf bifurcation threshold in terms of alpha is given by beta delta times beta plus 1 by beta minus 1. So in summary, this model system shows three different types of dynamics. One is that predator-free equilibrium point is globally asymptotically stable. Second, the coexistence equilibrium point is globally asymptotically stable. And third one, that is the two pictures in the lower panel, these corresponds to stable oscillatory coexistence, and these stable limit cycles are actually shown in green color. These are closed curve into these two panel. And one important aspect is that in this case what happens, that size of the limit cycle is quite large, and it shows that the attractor is pretty close to the horizontal and vertical axis. So that means the population remains at a low concentration for a significantly longer time period. So from the deterministic point of view, or if we ignore the environmental fluctuation and etc., then in this kind of situation we can say that population persists at all future time. But keep in mind that conclusion is mathematical. In reality, what can happen due to small environmental fluctuation or other demographic variability, one species or both the species may go to extinction. Why I'm talking about one or both the species? If it happens the prey goes to extinction due to environmental forcing, then as the predator is specialist in nature, that means it don't have any other food source, so automatically it will go to extinction. But if predator population goes to extinction, then what will happen? Prey will survive at its carrying capacity. Now the point is that in this kind of situation, from where this concept of transient dynamics comes into the picture. Now I'll go through that particular topic. So this is a typical time evolution of population density of prey and predator population. So initially they are started from these two values. One is from 0.3 for predator, and this is from 1.5 for the prey population, and we see that is a periodic oscillation that is observed over the time window 0 to 100. So of course you can see that that the size of this particular peak is little bit larger compared to the other peaks that you can see here. And another important aspect is that after initial burst, predator population remains or maintain a low density for a significantly long time and then start oscillating. But in between, they maintain some sort of low population density between two consecutive peaks. But where is the transient dynamics? Transient dynamics now you can observe. If we just choose different initial conditions, that is y0 equal to 0.25, blue color curve, y0 equal to 0.5, this is red color curve, and y0 equal to 0.75 for this yellow color curve. And you can see if we start from this initial density, then from this point to this point, so that means around 12 units of time, that predator population more or less maintain very low population density. If the initial population density of predator increases to 0.5, then this time period is much more longer. So that corresponds to red curve. And for this yellow curve, you can see starting from this position up to this position, it remains at a low level. So for this yellow color curve, by chance, if we cut our axis or stop our simulation at this point, it gives us some sort of indication that might be the predator population went to extinction. But actually, it maintains a very low level, takes a very long time to return back to some positive density, and then it shows some kind of persistent oscillation. And this is one example of transient dynamics depending upon the initial condition. There are different origins, reason, and mechanism for transient dynamics, but this one is the simplest example. Second example is this one. In this case, what I have done here, I have just plotted the solution of the system. That means the solution trajectory of the system for which are very close to the Hopf bifurcation threshold. One is before Hopf bifurcation, another one is just after the Hopf bifurcation. So in this case, what you can see, that population going to settle down to coexistence stationary state, but after significant oscillation with decaying magnitude, Here also it shows that it will converge to a small amplitude limit cycle, but the amplitude of the limit cycle decreases pretty slowly. And these are some mechanistic example. That means close to some bifurcation value. That bifurcation may be local, may be global, and depending upon the particular classification of the bifurcation, we can expect some kind of long transient in the system dynamics. So these are examples from simple Rosenwig-McArthur model, which is deterministic in nature. Now, if we consider a little bit complicated model in the sense that here we replace the that means prey-dependent functional response by predator-dependent functional response. And please excuse me for using some sort of different kind of notation in different slides, only for the reason because I have taken these pictures and results from different published papers, and that's why in previous problem X and Y are considered as population densities, but towards the end of my talk I'll use X and Y as the space variable. So please excuse me for these confusing notations. And in this case, U is the concentration of resource, V is the concentration of consumer, and apart from this ratio dependent functional response, here we have incorporated one more term, that is density dependent predator death rate, that is minus delta V square. So for this problem, dynamics is quite complicated. This is the complete bifurcation structure. I am not going into the details, but simply what we can say that local and global bifurcation curves divide the entire parametric domain into 8 different regions. So here the vertical black dashed curve is the transcritical bifurcation threshold. This magenta color curve is the saddle node bifurcation curve. This green color curve is the global bifurcation curve for the limit cycle, and this blue color curve is the Hopf bifurcation curve. This Hopf bifurcation curve and saddle node bifurcation curve, they intersect at the Bogdanov-Takens bifurcation point, which is a codimension 2 bifurcation, and on this Hopf bifurcation curve we find another codimension 2 bifurcation point, that is GH point, that is generalized Hopf bifurcation, or sometimes people like to call it as Boutin bifurcation point. So these bifurcation curves divides the parametric space into 8 different domains, and those are marked as R1, R2 up to R8. Now from here I am taking parameter value only from the one particular domain, where we can see that unstable equilibrium point that is surrounded by a stable limit cycle. So this is another example that in previously I have mentioned that you can see long transients in case of value very close to the Hopf bifurcation, that means onset of the Hopf bifurcation. In this case, this parameter value is far away from the Hopf bifurcation threshold, but still we have some sort of transient dynamics. What is the transient dynamics here? Because if we start from some point here that is very close to the unstable equilibrium point, it shows a long transient oscillatory dynamics before settling down to the stable limit cycle, and that you can see from here. So with respect to time, you can see that if we stop our simulation at t equal to 1000, it will give us a erroneous indication that it is stable. But if you perform the simulation over a longer time period, that is t equal to 5000, and you can see that it takes almost t equal to 4300 in order to settle down to the desired stable limit cycle. And this is another example of transient dynamics. So mostly people are interested to construct a mathematical model for ecology with some appropriate ecological justification, then finding out the equilibrium points, proving its stability, determining the bifurcation threshold, bifurcation condition, bifurcation curve, normal form of the bifurcation. But apart from that, there is something more with which researchers are nowadays very much interested, and these are such examples that is called the transient dynamics. Now we consider a delay differential equation model. This is a single species delay differential equation model. It actually models the growth of a predator species with which is actually subjected to alley effect. And this equation is also capable to show a wide variety of transient dynamics. I am not going into the mathematical detail of this particular problem. If you are interested, you can have a look at this work. And idea is that in this case, you can see that if we start from some initial condition, it shows a persistent oscillation for a quite significantly long time period before settling down to stable steady state. So this is one example of transient oscillation before settling down to stable coexistence steady state. And why this is called transient? This is called transient only for the reason because if you look at the some part of the dynamics which you observe at this range, this will not persist at large future time, and actual destination of the solution trajectory is a stable coexistence steady state, and that cannot be predicted from the dynamics what you can observe here. So by mistake, if we stop our simulation at t equal to 2000 or t equal to 3000, then we will have a erroneous indication that dynamics is oscillatory. Rather, it is actually a transient dynamics, and it's ultimately settled down to a stable steady state. And the point is that depending upon this transient dynamics, we cannot predict anything about the final destination of the solution trajectory, and also what is the shape and dimension of the final attractor. Because in the next picture, you can see that it actually settled down to the coexistence steady state, that means non-zero steady state. But here you can see after long transient oscillation, it actually settled down to zero steady state. So this corresponds to system collapse after a long time period. And also with another kind of parameter value, you can see after some persistent oscillation, it shows a different kind of oscillatory behavior at large time. And there are other complexity also, like this, what you can see that initially it shows some kind of irregular oscillation, and ultimately it settled down to a chaotic oscillation. So these are several examples of different kind of transient dynamics. Now, there is another kind of problem which is very much important to consider in the context of ecology, that is dynamics of a system with slow first time scale. So in general, now question arises that why we are interested to consider the slow first time scale dynamics, and is it possible to observe such kind of dynamics in nature? Answer is yes. This is an example of the population density of spruce birdworm, and which is actually collected over a 30 years time period. And you can see that this spruce birdworm remains at a very low population density for a significantly longer time period before showing some sort of oscillatory behavior. And this kind of solution trajectory we have observed earlier in case of Rosenwig-McArthur model also. And one particular explanation of this kind of solution trajectory is that sometimes it may happen that resource and consumer, they have significant amount of growth over to different time scale. So if we measure the growth of resource and consumer over the same time scale, then it may happen that growth rate of one species is much more faster compared to the growth rate of the other. And as a result, we need to consider the dynamics with slow first time scale. Now, how it can be done? Just for example, in case of Rosenwig-McArthur model, we can rescale the parameter for predator growth, assuming that growth of the predator is slower compared to the growth rate of the prey. And that's why we can have this modified Rosenwig-McArthur model with slow first time scale, where epsilon is the measure and it actually the ratio between the growth rate of predator over prey measured over the same time scale t. And in general, epsilon is lies between 0 and 1. And people who are working in the area of mathematical ecology or nonlinear dynamics, they are quite interested in the system dynamics in case epsilon is much less than 1. So keep in mind there are two aspects. Number one, mathematically it is interesting to understand the dynamics when epsilon is much less than 1. But on the other hand, question may arise that in reality, is it possible that epsilon is much less than 0 or not? Answer is actually it is not pretty close to the 0, but there is a significant difference in the time scale in the growth rate of two species. Now, if we look at the solution trajectory, that means how this parameter epsilon affect the system dynamics. So this is one example. On the left panel, you can see the dynamics with epsilon equal to 1, and without changing any other parameter value, if we just change epsilon from 1 to 0.1, then we can see this kind of dynamics. And if you just try to understand that how this dynamics looks like, so one trajectory starting from this point, it moves more or less in a horizontal direction. Then there is a small bend through which trajectory transfer from horizontal line to this vertical trajectory. It remains in the vertical position for certain time period, and again you can find a small bending here, and that means it leaves this vertical trajectory which is pretty close to the vertical axis. Keep in mind this motion is not along the vertical axis, but it is a motion very close to the vertical axis, and that's why it can come out from this vicinity, and then it moves again in a horizontal direction, and finally it moves along the non-trivial null line. This is the black color curve to reach the stable equilibrium point. So this is the case where you can see the transformation in the solution trajectory as epsilon changes its value from 1 to 0.1. In case of periodic solution, what you can observe, again, you have similar kind of dynamics, but now here coexistence equilibrium point is unstable, and that's why it ultimately settled down to this particular periodic solution, and this is actually called relaxation oscillation. Now the question is that from where we can understand that how trajectory or what will be the nature of the solution trajectory, or can it be analytically proved that solution will be consisting with this kind of horizontal line, vertical line, and some part of the manifold? Answer is yes, and this is the just time series for slow first time scale dynamics. And this is the limiting case if epsilon equal to 0.01. So if we make the limit epsilon tends to 0, then it will be a pretty close curve, which is a closed orbit, and more or less remain within the vicinity of this particular curve. Now, from where we can understand the dynamics, we can actually consider the first system that is governed by this equation, where with respect to first time, we have chosen epsilon equal to 0. And dynamics of the system can be understood quite easily, because from here you can find Vt equal to V0, and in terms of V0 as a parameter, you can understand the dynamics of this system. And of course, you can find out the equilibrium points of this system with V0 as a parameter, and also determine its stability. The main concept is that for this layer system or fast subsystem, predator population remains density remains constant for significant time period, and the trajectories are more or less horizontal lines. On the other hand, if we write down the equation in terms of slow time scale, then we will have the dynamics of the system in terms of slow time tau, and the reduced system, that means with epsilon equal to 0, its governing equation is an algebraic differential equation. And these consist with a vertical straight line and a parabolic arc, which determines the nature of the solution. And here is the summary of the result, that what are the different terminology, what is critical manifold, what is critical fold point, and where dynamics is slow, fast, so many things. These are summarized here. The main point what I just want to draw your attention, this is the solution corresponding to fast system, and this is the solution corresponding to the slow system. And as a result, if we look at the dynamics of two systems separately, so this is the dynamics of the fast system. And as a result, you can see the solution trajectories are horizontal. For certain range of initial condition, you can find equilibrium points. These are unstable equilibrium, and these are stable equilibrium points. This is the dynamics of the fast system. And second one is the dynamics of the slow system. As I have mentioned, that this consists with this vertical axis and this non-trivial pre-null. This magenta color point is called the fold bifurcation point, and this magenta color curve is a transcritical bifurcation point. All of this can be obtained analytically. And for a particular choice of parameter, what happens, that final attractor is the concatenated solution trajectory obtained from slow system as well as fast system. And if we combine these two, that means dynamics of the slow system and dynamics of the fast system, then we can see this kind of phase flow. So that means if we start from some point here, it will start moving in this direction, then it will follow this line, or it will leave this position depending upon the fact whether it is stable or unstable. In this case, this branch is stable, this branch is unstable, and that's why if you look at some solution trajectory here, they are approaching towards this curve, whereas with respect to this branch, they are approaching away from it. And here you have this kind of direction, and as a result, if you combine, you will get the complete solution trajectory in the combined form, as you can see here. And one more interesting aspect is that it shows some sort of Carnot explosion. So that means due to small change in the parameter value, all of a sudden small size limit cycle drastically change to large periodic solution, and that is called Carnot explosion. And this is one example that if we change one parameter value slightly, then this small amplitude limit cycle suddenly jumps to this large amplitude Carnot cycle. And what is interesting here, that this closed orbit is consisting with some part of the stable critical manifold, and some part remains pretty close to the unstable critical manifold. And once the solution trajectory jumps from this stable critical manifold to the horizontal flow, that is actually called relaxation oscillation. And this jump, that is Carnot explosion, from the small amplitude limit cycle to large amplitude limit cycle, can be clearly visualized from this bifurcation diagram. Here you can see with the change in the parameter value within this small narrow region, this small amplitude limit cycle suddenly becomes large amplitude limit cycle, and this is called Carnot explosion. And Carnot explosion that takes place within this small interval, which is marked in red color here. And also, depending upon the complexity of the model, you can have different structure of this Carnot oscillation and also relaxation oscillation. This is our another work where we have shown that Hopf bifurcation threshold that can be shifted with the variation in magnitude of the slow fast time scale parameter, that is epsilon. In earlier case, Hopf bifurcation threshold is independent of epsilon. Here it is depending upon epsilon. And as a result, you can see this null line is a oblique straight line. In previous case, it was a vertical straight line. And this is the consolidated diagram for the slow fast dynamics. This double arrow corresponds to fast dynamics, and single arrow corresponds to slow dynamics. And here also we have shown some other kind of result, that what is the entry point and exit point. Entry point and exit point means the points at which the solution trajectory leaves the fast subsystem and moves towards the slow subsystem, and again it leaves the slow subsystem and return back to the fast subsystem. Some time ago I have mentioned that although you can see that solution trajectory is pretty close to the vertical axis, but it is not exactly following the vertical axis, and actually a zoom version of that solution trajectory you can see here, that this line seems to be more or less along the y-axis in earlier picture, but there is an infinitesimal distance between these two. As a result, it can return back from this vertical position to this horizontal position and again enters the first flow and move in the horizontal direction towards right. And what I have mentioned that in which we are interested to understand the limiting solution trajectory as epsilon is very, very small. And this is one pictorial representation. Red color curve is the solution trajectory, that means relaxation oscillation for a small value of epsilon, but not very close to zero. And limiting relaxation oscillation, that is shown here in the blue color. So in this case, this blue color curve is a part of the vertical axis, and this relaxation oscillation is the concatenated version of the slow and fast flows, that is two horizontal lines from this point to this point, and another horizontal line from this point to this point, and two part of the slow flow that is starting from this point along the parabolic arc up to this red point, and also starting from this red point to up to this point. These are actually corresponds to the slow flow. So this is all about slow fast time scale dynamics in the context of temporal model. Now quickly I show you that some of our recent result on spatiotemporal pattern formation, and why I'm talking about these things within this talk, because it also shows significant amount of alteration in the transient dynamics. So in this paper, what we have considered the simple that Rosenick-McArthur model is modified with three aspects. Number one, alley effect in prey growth, then slow fast reaction kinetics, and then reaction diffusion equation. So far as our knowledge goes, there is very few work in this direction, that is effect of slow fast time scale on spatiotemporal pattern formation. And in this work we have proved several results, but here I am just talking about briefly about the change in the traveling wave solution for the system as epsilon changes. So this is an example of a monotone traveling wave joining coexistence steady state with the predator free steady state. This is a non-monotonic traveling wave joining the coexistence steady state with the predator free steady state, because this red curve corresponds to predator population, blue curve corresponds to prey population. It is 1, this is 0. So it clearly joins the coexistence steady state with 1, 0. And after certain bifurcation, this non-monotonic traveling wave changes to periodic traveling wave. But here you can see some kind of transient non-monotonic fluctuation. And this is a particular plateau, and where this plateau comes from, and how long it will remain on this particular steady state, that completely depends upon the background parameter. And as you can see here, that if we change the initial condition, instead of perturbing from 1, 0, if we give perturbation from 0, 0, so then first it will move towards 1, 0, and then it will enter to this periodic oscillation. And in this case, what you can observe, that before going to this periodic traveling wave kind of motion, it shows a transient dynamics that remains at this level for significantly longer time period before converging to this periodic motion, which is actually periodic traveling wave. And these are some other examples, that means how transient nature is changes. That here you can see the nature of oscillation, that means amplitude of oscillation is quite large because wave number is quite small here. And here you have prominent oscillatory transient dynamics before it settled down to this final destination. And this is also, you can see that transient dynamics in magnitude, in periodicity, in amplitude, they changes significantly with parameter values. Just for limited time period, I am not mentioning each and every parameter values, but if you are interested, you can have a look at our work to get all the details, what initial condition, what boundary condition we have used, what are the parameter values, what are the effect of initial condition on the system dynamics. But finally, what I just try to summarize here, this is the traveling wave for epsilon equal to 1. This is the traveling wave for epsilon equal to 0.1, and this is the traveling wave for epsilon equal to 0.01, if I recall correctly. It might be this is for 0.5 and this is for 0.1. But the point is that if we move from this picture to this picture, so it is from epsilon equal to 1 to some small values of epsilon 1. And here you can see that the transient dynamics, that is before showing some sort of oscillation, system remains at the value 1, 0 for a significant time period. That means the time required for the population to move from this position to this position before starting oscillation, it is significantly increased with the presence of slow fast time scale. And this is another example of effect of slow fast time scale on pattern formation in 2 dimension. So what you can see that interacting spiral pattern can change to just a tip of the single rotating spiral with the decreasing magnitude of epsilon. And not only it will change the pattern, it also alter the overall fluctuation in the population level that you can see here. This is the plot of the time evolution of spatial average population density with respect to time for both prey and predator. And you can see it moves from spatiotemporal chaos to quasi-periodic oscillation in terms of spatial average population density. So this is not only it affects the transient dynamics, it also changes the qualitative pattern forming scenario for interacting population model. And I must stop at here without saying anything more. So future direction is that these are some listed here. So apart from that, what we are trying to do, we are just trying to extend this result to some other kind of dynamics of the system which shows some sort of catastrophic shift or regime shift, and also the dynamics of the system for delay diffusion model, and we are interested to study the effect of slow fast time scale. So these are some future direction or challenging question, whatever maybe you can consider it. And these are some references where you can see some sort of details about the transient dynamics and other things. And these are some of our work. If you are interested, you can have a look at it. And I must thank my collaborator, that is Tapon Shaha in the Presidency College, Kolkata, Pallab Jyoti Pal, he is also my collaborator, 3 foreign collaborators, Sergei Petrovsky, Vitaly Volpart, Andrew Morozov, and this is my current PhD student, Pranali. She actually did most of the part of the work that I have presented at the end for Bulletin of Mathematical Biology paper, and other works are carried out by these co-authors. Thank you very much for your kind attention.
So thank you, Professor Banerjee. It was a wonderful talk and lots of information. The audience could get it. So it's really, really very useful talk and wonderful lecture. So, we can have some question, few minutes we can spend on question answering. Is there any question from audience? Yes. Is there any question?
No, Junior, the participants should ask.
Yeah, participants, I welcome any question if you have in your mind, please ask. And though Professor Banerjee has mentioned that many articles he has showed, anyone can go through the articles and can understand more. But right now we can afford to discuss on 1 or 2 questions.
Malay, hello.
Yeah.
This is Subit Das.
Yeah.
Excellent talk, just excellent.
Yes,
Excellent. I want to know about temporal spatial model, which has been published in Calcutta Mathematical Society. You have shown it.
No, it is actually published in Bulletin of Mathematical Biology.
Oh, sorry, Bulletin of Mathematical Biology. Okay, that is temporal. Can you go to that?
Okay. So I have to share.
It is actually merging up to diffusion equation, reaction diffusion equation. What I am saying.
Yes.
Now, how you are correlating with the
Yes, this one.
I can't see actually. It is very interesting model. Mhm.
For transient model.
Uh-huh.
Can you
Is-
see my screen now?
No, I can't see actually.
I already shared my screen.
Yes. Now I think.
Now it is coming.
Yes,
Uh-huh.
you can
This
see
one.
now.
You see, this is the actually reaction diffusion equation. The first one, but
Yes.
the addition of UV by 1 plus alpha U.
Yeah.
How you are connecting this one, these two? Hello.
I'm not getting your point.
No. How you have? What is the motivation of using UV by 1 plus alpha U minus 1? And you are merging to diffusion equation, correct? Na? Reaction diffusion
Yes,
equation.
yes. Because
Uh-huh.
this is the temporal part actually takes care of the interaction between the individuals, and this diffusion actually takes care of the random movement of the individual over their habitat. So this is the idea. So it can be derived in a way that population at a particular location and at a particular time point can change due to two different type of phenomena. One is the demographic phenomena like birth, death, or in case of prey, that is predation by the predator. So with respect to time, it can change. And also it is possible that individuals who were at the position x minus delta x, they can come to the position x within the time period delta t. So if we consider the growth or decay of the population with two different mechanisms simultaneously, one due to demographic phenomena like birth, death, predation, etc. And second is the immigration or emigration, that means movement of the individuals from one location to other location. If you consider these two phenomena together, and as a result, you can have this reaction diffusion equation. So demographic part is taken care of by this reaction part, and movement from one location to other location, that is dispersion, that is taken care of by this diffusion equation.
And what about the UV by 1 plus alpha U? I'm just
UV by 1 plus alpha U, that is actually U by 1 plus alpha U is the saturating functional response. So the amount of prey consumed by the predator is not an unbounded function. Mostly in case of Lotka-Volterra formulation, what is assumed that with the increasing amount of prey, there will be higher amount of consumption. But that is not true. There is a certain kind of saturation. They cannot consume their food item after a certain threshold, and that's why the saturation level is modeled by U by 1 plus alpha U. And its mechanistic derivation is given in the book by Mark Cott, that how this functional behavior is achieved. And if we assume that predator don't need any time to handle the prey individual, then you can consider alpha equal to 0, and we can go back to the Lotka-Volterra formulation.
And no, you are taking the second one. You have taken epsilon, considered epsilon there.
Yeah.
In some model, you have considered whole epsilon, whole the right hand part into the epsilon.
Yes.
So
That is
here
due to the slow first time scale.
Slow fast. So you can do also that one.
Yes.
Okay. It's okay. Very good.
Sir,
Very
I
good.
have a question.
Yeah, please.
If the epsilon is always less than 1, is that 1 is the upper bound of epsilon?
Actually, this comes from very simple idea that whether predator growth rate, when measured with respect to the time t for you, is greater or less. If you because you are correct, there are two different aspects. So epsilon greater than 1, epsilon less than 1. So it is a customary that if growth rate of prey is slower than predator, then epsilon will appear into the growth equation for you. And if growth rate of predator is slower than the prey, then epsilon will appear into the second equation.
Correct.
Okay, sir, one more thing. In the first paper of slow first method, you have taken epsilon is equal to m, that means the death rate of predator. But in the rest of the two papers, you have included delta v. So is there epsilon delta less than 1 or only the epsilon less than 1?
Actually, it completely depends upon how you are non-dimensionalizing the model and how you are scaling the parameter. So you can do two different things. First, you can non-dimensionalize your model system, and then you can estimate the parameter value One, you can see the parameter estimated for the predator population is significantly small compared to the parameter value estimated for the prey. So then in order to work with a significant number of digits, you can take out a factor epsilon, or you can actually consider epsilon as a growth rate of predator over the growth rate of prey, which is in case of Rosenuk-McArthur model, it is because M is a dimensionless parameter, but in terms of original parameter, it is actually death rate of predator over the growth rate of prey, which measures the time scale between the growth rate of two species.
Okay, so thank you. It was wonderful discussion also. And thank you, Professor Banerjee.
Hello.
And since now we are having the next lecture.
Sir, I have a question, if time permit.
Actually, we are already late for the next lecture. But anyway,
just one question.
Yeah. So Anna, you can raise your question so that discussion can go on after this. All lectures are over today. So
Okay,
please, you give your.
Sir,
question.
actually, I have not a lot of idea in partial differentiation, but we are looking some nice figure which are look like the fractals. So I just asked, there are any article between the relation of your paper?
Actually, you are correct, because in order to characterize the dynamics of the system, one can of course calculate the fractal dimension of those attractors.
Okay, thank you, sir.
So thank you very much. Let us once again give a big applause to Professor Banerjee for his excellent lecture. So thank you. We'll be happy to listen to you again. So thank you very much.